So here we have to give some examples on equivalence classes in an equivalence relation. So the example is, suppose it is asked to show that the relation the relation R in the set Z of all integers. So Z is a set of all integers. It means R is a subset of Z cross Z. So R is a relation in the set Z of integers, which is given by R equal to R consists of all the ordered pairs A comma B, such that 2 divides the ordered pair A minus B. So we have to show that this relation R is an equivalence relation. So it is an equivalence relation. We have to show this. So now here A comma A should belong to the relation R. Since why? Since A minus A is equal to 0. So so 2 divides 0. So 2 divides 0, obviously. So therefore means 2 is a factor of 0, obviously. So therefore, so I can say, so R is a reflexive relation. So R is a reflexive relation on the set Z. And also, and if A minus B equals to some 2n, suppose, where n belongs to some Z, then B minus A also will be equal to 2, will be equal to minus 2n. So A minus B and B minus A both are divisible by 2. Both are divisible by 2. If A minus B equals to some 2n. So therefore, if A comma B belongs to the relation R, then this also implies that B comma A also belongs to the relation R. So I can say, so actually first we have to show that this given relation R is an equivalence relation, and then we have to find its equivalence classes. So if A comma B belongs to R, then it implies B comma A also belongs to R. So I can say, so R is a symmetric relation. R is a symmetric relation, and also I can say that, and if A comma B belongs to R, means that A minus B equals to some n, and some B comma C also belongs to R. It implies that B minus C also equal to some 2m, suppose, for some m comma n belongs to Z. So now A minus C, that I can write it as A minus B minus A minus B plus B minus C, obviously, which is equal to 2n plus 2m. So which will be equal to 2 into m plus n. So I can say that, so m plus n also belongs to Z if m comma n belongs to Z. So I can say that A minus C also will be even, also will be divisible by 2 if A minus B and B minus C R divisible by 2. R divisible by 2. B minus C R divisible by 2. So I can say that, so the relation R is a transitive relation also. R is a transitive relation also. Now hence we can say that, so R is transitive and it is symmetric also and it is reflexive also. So I can say that R is an equivalence relation. R is an equivalence relation in the set Z. Now we have to find the equivalence classes. So here we can see that, um, suppose we take E. E is the set of all integers, suppose. Set of all even integers, suppose. Even integers. And O is the set of all odd integers. Set of all odd integers. So then we can say that, then we know that even number minus any even number will be equal to even number, and odd number minus odd number, if you do, that will be also equal to even number, and odd number minus even number, or if you do even number minus odd number, that will be equal to odd number. So we can't get even. So it means that we have to get even number since it should be divisible by 2. So it means that all even numbers will belong to the relation R. It means that all even numbers will be related to each other in the ordered pairs in the relation R, and in all odd numbers also will be related to each other in the relation R, but any odd number will not be related to any even number in the relation R. So I can say that all even numbers will be related to each other, related to each other in the relation R, and all odd numbers will be also related. Odd numbers will be also related to each other in the relation R. Also related to each other in the relation R. But odd number will not be related to any even number, but any odd number will not be related, will not be related to any even number in the relation R. The relation R. So I can say that, okay, so I can say that E is a subset of Z, and the set O is also a subset of Z, and so I can say that E union O, that is equal to Z, but E intersection O, that is equal to phi. It means that there is, since E is a set of all odd numbers, E is a set of all even numbers, O is the set of all odd numbers. So they are the two disjoint sets. So therefore the subset E, therefore the subset, therefore the subset E of Z is called the equivalence class containing 0. Equivalence class containing 0 or any other even number. So any other even number and is denoted by the equivalence class 0, or you can write it as 2r, where r belongs to z. Since why it should be even number. And also O, the subset O is called the equivalence class containing 1. It's called the equivalence class. It's called the equivalence class containing 1 or any other odd number. And is denoted by 1, which is equal to 2r plus 1. R belongs to Z. So, um, so this concept of equivalence class is applicable only for equivalence relations. So the rule, we can say the rule for equivalence classes. So the rule is that um, given any equivalence relation R, given any equivalence relation R in on the set on a set X, it means that R should be a subset of X cross X. Then R divides, then R, the relation R, obviously it will divide the set X into mutually disjoint sets, into mutually disjoint subsets AI, which are called the uh, partitions. And these AI are called the partitions or subdivisions of X, partitions or subdivisions of the set X, such that all the elements of the set AI are related to each other, and are called, equivalence classes, and so are called so they are called equivalence classes. And no element of AI is related to any other equivalence class AJ, and no element of a particular equivalence class, no element of a particular equivalence class AI, no element of a particular equivalence class AI is related to any other element, is related to any element of any other equivalence class AJ in the relation R, in that relation R, where I should not be equal to J. And the third rule is that the union of all those AJ equivalence classes will give us the set X on which the relation R has been formed. And AI intersection AJ, that should be equal to phi, where I not equal to j. Since why all these equivalence classes should be mutually disjoint subsets. They should be mutually disjoint subsets of X. So we can give another example on this. That is, suppose if we define a relation R on the set Z, example, we define a relation R on the set Z such that R consists of the ordered pairs A comma B, such that 3 divides A minus B. 3 divides A minus B. So now we can say, now the relation R divides the set Z into three into three equivalence classes here. Into three equivalence classes, which are A1, A2, and A3. Where A1, I can say it is the equivalence class which are related to 0. It means which consists of all the multiples of 3. A1 is the set which contains all the multiples of 3. It means it can contain 0, 3. Actually, it will be on the negative side also. Means it will be like dot dot -6, -3, 0, 3, 6, etc. So this the equivalence class A1 contains all the multiples of 3 which are related to 0 and which is 3R, where R belongs to Z, obviously. And A2 is the equivalence class which contains the elements which are related to 1 and which are related to 3R plus 1. So actually it is the set of all the elements which are like -5 and then -2 and 1, 4, 7, etc. So where R belongs to Z, obviously. And A3 is the equivalence class which contains all the integers which are related to 2, which are actually 3R plus 2, I can write. So it means which is the set of all the elements which are like -4, -3, sorry, -4, -1, 2, 5, 8, etc. This is where R belongs to Z. So A1, A2, and A3 are the three equivalence classes here in this case. So hope you have understood that whenever we have an equivalence relation R on some set A, then we can separate that set A into some equivalence classes which are mutually disjoint. It means that their intersection should be phi. Means A1 intersection AI intersection AJ should be phi. So they should be mutually disjoint subsets of the set X. AI should be obviously a subset of X actually for all I. Okay, so hope you have understood the concept. Thank you.